We're actually going to use several models for gravitational force over the course of the semester, and this is the first one, which is why it's gravitational force 1. The force exerted by gravity can be described as the mass of an object multiplied by the acceleration of that object caused by gravity, the gravitational acceleration. This is what we call the weight of the object. Near the surface of the Earth, the value g, little g, acceleration due to gravity, is close to constant. In a very approximate way, the Earth is flat and infinite, and therefore we can do a lot of day-to-day calculations using the assumption that our value of little g is constant, which is really equivalent to assuming the Earth is flat and infinite. We know that's not true, so if we start working with things that are going far from the surface of the Earth so that the Earth no longer looks flat, as it does when we're close up to it, then we need to find a different formulation of gravity, and we will. We'll do many of those sorts of calculations. Gravity always points towards the center of the source, which we call the center of gravity. It is coincident with the center of mass, which relates back to our very, very, very opening discussion about extended versus point bodies. And so, for point body purposes, gravity acts as if it emanates from the center of mass, which is why we call it the center of gravity. Formulaically, that force is what we call the weight, and that weight is equal to the mass times the acceleration of gravity, little g. That is a constant force, so it's a good working example of a constant force, and we will use it in several problems, as well as looking at some other problems. An example of a variable force is Hooke's law, named after Robert Hooke, who was a very early microbiologist who also did some physics, or he was a very early physicist who also did some microbiology, depending on your perspective. The force exerted by an object is proportional to the stress or compression. Now, all materials are a little bit elastic, and every material, even ones that appear very elastic, tend to deviate from this at extremes. So it is possible to stretch a rubber band so that it never returns. And it is possible to stretch a spring so that you do damage so that it never returns. That's called the elastic limit. But even for things like solid steel bars, which to our sort of macroscopic way of life don't seem particularly stretchy, actually do behave very much in this fashion as well. So you can stretch, it's applying a stress, or you can compress any object to some extent or another, and over some range, most objects obey some variation of this formula, so that the applied force causes a stretch, and then the spring, or other object, reacts to that by creating a force in the opposite direction, hence the little negative sign here, but which does have the same magnitude, that is proportional to the amount that you stretch it. And we will use this in chapters not very far in your future to develop a very nice little model of atomic forces and matter. So this covers the introductory section for chapter 2. There will be, of course, homework problems. We'll do in-class problems. We'll work with these things, and we'll look at a number of other things. And there may be additional